All right, so all of 8.2 was estimating a population proportion. So we did p hats and p's, and that means we're talking about a decimal or a percentage or like a number of people out of a total number of people who believe something. Okay, and now we're talking about estimating a population mean. So we're talking average. And so this is just the general formula for any confidence interval, right, that we've talked about over and over again. The statistic plus or minus critical value times the standard deviation of the statistic. So when we were doing the p's, it was the p hat plus or minus z star for your critical value times the standard deviation of the statistic, which looks like this. Okay. So for the formula for estimating a population mean, what do you guys think the statistic's going to be instead of p hat? It's going to be x bar. Okay. And the critical value is z star, only if we know one thing, which we will talk about. And then for standard deviation of the statistic, it's no longer the p hat formula here, right? Anybody remember the formula we used in chapter 7 where we could find the standard deviation of x bar? Yep. Okay. So the standard deviation is actually sigma over the square root of n. That's what we learned in chapter 7. That would give us this guy's standard deviation. One important thing to note, sigma. You need to know what sigma represents. This specific symbol is the population standard deviation, not the sample standard deviation. All right, sigma represents the population standard deviation. So when we did the mystery mean activity, we were estimating mu, the true mean, right, by getting an x bar, and they actually gave us the fact that the population distribution was normal and its standard deviation was 20. This is not normal, okay? If we don't know the true mean, do you think we're going to know the true standard deviation of the population? No. No, okay? Now, if you do, sometimes you do, this is called a one-sample z interval for population mean, and you might want to write that down. All right? So one sample z interval for population mean. You're going to use this if you know sigma, which is the population standard deviation, which is not very often, okay? But sometimes we do. So again, the problem of the unknown sigma. If we don't know the population mean mu, then we don't know the population standard deviation either. So what do? We use what's called the standard error of x bar. So we replace the standard deviation with s sub x. So instead of sigma, we use s sub x. What is s sub x? It's the sample standard deviation. And again, SE sub x bar stands for standard error. All right. And replace your sigma with S sub x, which we can get from our sample. And what happens is we get a different distribution called the t distribution with n minus 1 degrees of freedom, which we will talk about. So the standard normal curve versus the t distribution. So we're going to use the t distribution when we don't know sigma, which is majority of the time, all right? So most of the time when we do means, you're going to be using the t distribution. Some things that you want to write down. Similar shape, okay? Standard normal curve and t distribution both have a center at 0, okay? They both are bell-shaped and symmetric. However, the spread of the t-distribution is a little bit greater than that of the standard normal. So what we're looking at here, the purple line is the standard normal. So it comes pretty high right here, and it's lower in the tails. And these two right here are both the t-distribution. So we've got this dotted line, that's the t-distribution, and we've got this like aqua colored line, that's the t-distribution with different degrees of freedom. And degrees of freedom are related to your sample size. Okay? So important thing to note, t-distributions have more area in the tails. So notice these two right here, these are the t's, and there's actually more area in the tail for the t-distribution than for the standard normal curve. Okay, the standard normal curve is a bit higher. So the t-distributions have more probability in the tails and less in the center than does standard normal. This is because we're substituting in an estimate for S of x instead of sigma. So there's more variation in the statistic. Okay, another important thing to note, as the degrees of freedom increases, so as your sample size increases for your t-distribution, it's going to get closer and closer to the normal curve. All right. So the more people we have in the sample, our S of x is going to better estimate sigma. Some of you may want to write a couple notes down about this. You got a few things? Okay. All right. So most of the time, we do not know sigma. If we don't know sigma, we replace this with S of x. Guess what else changes? This right here. We're no longer using z star. We're using t star. Okay? It's a different distribution. This should say x bar plus or minus t star times S sub x all over the square root of it. Okay, just a reminder that this piece right here is called the standard error. And this entire part right here, anybody know what that's called? Same as before. Margin of error. So whatever you're adding and subtracting, the total of that is your margin of error. So we're going to talk about how to find t star. So a z-score comes from a general formula that we've used back in the day in chapter 2, the data point minus the mean divided by the standard deviation. T formula, really similar, but instead of this standard deviation, we are using standard error. Okay, same formula, but with standard error. All right, what critical value, t star from table B, should be used in constructing a confidence interval for the population mean of each of the following settings? So we use what's called table B, which will be given to you on the test. You can also use your calculator. There's two ways to do these. I'm going to show you both ways. So table B, you guys find in the back of your book. It's right by table A. All right, and we'll figure out how to find our t star given a 95% confidence interval based on a simple random sample n of size 12. All right. So you guys, we do our 95% the same way, where we're looking for the tails. And so you think of it as split, just like the normal curve, where the 95% is here and here. And so how much area is in the tails? 5%, and we divide by 2. So each of my tails are 2.5%. And so we have 0.025 for our decimal. So if you look at the top of table B, that's where those decimals are. So you're looking for 0.025 at the top of table B. All right. Now my sample size is size n. Degrees of freedom, and you should probably write this in your notes. We always write df is always equal to n minus 1. It's just your sample size minus 1. So in this case, our degrees of freedom is 11, okay, because our sample size is 12. So on the left-hand side of your table, you want to find 11. It says df. Those are your degrees of freedom. So everybody find 11, scroll over to 0.025, and that is your T star critical value. And so everybody put your finger on that and see if you get the right one. 11 and 0.025. Did you guys get 2.201? Yep. That is T star. That represents the standard deviations away from 0. So like you have a negative 2.201 and a positive 2.201. Okay. All right, for 90%, okay, 90%, what's the decimal we're looking for at the top if it's 90%? 0.05, because we do 10% divided by 2. So we have 0.05. And if I have 48 observations, notice what happens when you get into the 40s. You either get 40 or 50. Always round down. So we're going to actually use degrees of freedom 40. It's the more conservative answer. Okay? So you go to 40, scroll over to 0.05, and what do you guys get for T star for this guy? 1.678. Okay? That's what you should get. All right. That is table B. Good times. There is probably an easier way, and I would probably do it this way, which is inverse T on your calculator. 1.604? I'll believe you. Here's 40. Oh, we've got our percents down here. Here's a 90. This guy. Yeah. Oh. What? All right, I believe you. All right, inverse T on the calculator, you guys. This is a better way to do it, just like inverse norm. You can use table A for the Z star too, but I always just use my calculator because that's me, and you just get in the habit of it. I don't know. Either way is fine. So basically, we want to go to, if I can find my calculator. Menu, statistics, distributions. Okay, just like where we find all our other distributions stuff. And we want to go to inverse T. And we just plug in area and degrees of freedom. So let's do the one we just did. This is going to be a more accurate answer since our table only does 40, right? So we were doing the 90%. So we do 10% divided by 2. So what do I plug in? 0.05. And we are going to do our most accurate degrees of freedom. So we had 48 for our n. So our degrees of freedom is 47. And this will give us a better T star. That's why I have this answer in my paper. All right, this is slightly more accurate than your book because of the rounding when your book gets to the higher numbers. Did you guys find it? All right, we're not going to do the whole test today because we don't have time, but we are going to talk about the conditions. All right, so the plan step for estimating mu, your interval, is the same as the plan step for your p, except for one slightly different thing. So you have to check for random. You have to check 10% condition, which is this guy. If you're sampling with replacement, you technically don't need to check the 10% rule. It's only when you're sampling without replacement, which most of the time we are sampling without replacement, okay? And then we check normality. For p's, that's np greater than or equal to 10, n times 1 minus p greater than or equal to 10. What do you guys remember for means? Greater than or equal to 30. there is one thing to add. Let's say it's not greater than or equal to 30. You can actually check the graph. All right, check graph of your sample data. Okay, if you have no outliers or strong skew, you're allowed to have a little bit of skew. Okay, no outliers or strong skew, then you can still say it's normal, all right? As long as there's no outliers or strong skew, even if you don't have greater than 30. So for example, let's look at these graphs right here. This is a sample size of 20. So we don't have greater than 30. All right. This first graph, does it have strong skew or outliers? No. Everybody say no. No. Okay. Nope. And so you're good to go, even though you have 20. You can still say normal. Okay. How about this guy? Strong skew or outliers? Good to go. All right. And this is the best one to check. I prefer this one. Do you guys remember the name of this? Not the residual, the normal probability plot. It tells you if it's normal by how linear it is. Residual should be random scatter. Remember that? All right. So if you see like it's pretty much linear, you're good to go. All right. So here's ones that don't work. Only one of these works. Which is the best one? The middle one. This is the most normal. This one has outliers, so it's a definite no. And this one has strong skew to the right. Okay? All right, so to be safe, only use a t-distribution for small samples when there's no outliers and no strong skew. Okay, so you can proceed as long as you have no outliers or strong skew if your sample size is under 30. If it's over 30, you don't need to check the graph. All right, let's see if our conditions are met. So random, 10%, large counts. So this first one, we're estimating the average GPA of students at your school. You randomly select 50 students from classes you take. Do we have a random sample? No, we don't have a random sample because you're sampling from classes you take, right? Not all classes. So this first one, it doesn't even matter what the graph is. We don't have a random sample, so it's missing that. All right, this next one is, it's been a while since we've seen one of those stem and leaf plots. Okay, you got to look at this shape of this graph. What is it? It is skewed left. So, and that's pretty strong skew, right? So have our conditions been met? No. All right. And this last one, SAT math scores for a random sample of 20 students at a large high school. What do you guys think? Yes, it is moderately skewed right, which apparently is okay. I agree with you. Everyone got so mad at me last year for this too. They were like, what? You can proceed with caution. Okay? Proceed with caution. So don't forget that if you're calculating confidence intervals, all the conditions have to be met, and you have to state them all. You guys already know that, so we're good to go.